So here we have Taylor and Maclaurin series, a lesson that brings us full circle back to where we started this whole entire module. Remember, we started with Taylor polynomials. And now, what if we took that Taylor polynomial and we just kept going with it, right? Okay, that's what we're doing here. You can see that we plan to represent functions with a power series, which is what we did in the last lesson. Taylor or Maclaurin series. We're going to tie this whole entire unit together in a nice, neat package. Before we do that, we need to step back in time. Warm up number one, right? The fourth degree Maclaurin polynomial for f of x is equal to e to the x. So remember that Maclaurin is essentially the same thing as Taylor, but we center it at 0, which, for most cases, that's just the easiest thing to do. So we start this thing by taking specifically 4 derivatives of e to the x, and we're going to evaluate all of them at x is equal to 0. So this is, of course, the toughest thing that you're going to do all day, because, let's see, e to the x here, and the derivative of e to the x is e to the x, right? And then the second derivative there is also e to the x, right? And I don't even care. All the way to the fourth derivative of e to the x will be equal to e to the x. All right, now you want to evaluate each one of these, the function and its derivatives, specifically at x is equal to 0. So f of 0 is e to the 0, which is equal to 1, which means that f prime of 0 is equal to 1, and f double prime all the way down. I turned that into an exclamation point because why not? All right, that's also equal to 1. A whole bunch of 1s. Okay, so here then I'm going to put all of this stuff together in the formula for a Taylor polynomial centered at 0, which makes the Maclaurin one. So it goes like this. So we want fourth degree. In general, I would write something like this. I would start with the f of 0. I guess this should be like m sub 4. Okay, f of 0 plus, then we do our derivative, f prime of 0 times x. And, if we stopped right here, we basically have a tangent line, right? That is the first degree Taylor polynomial plus f double prime of 0, and then we divide that by 2 factorial. So actually what happens is that this one's divided by 1 factorial, and this is divided by 0 factorial, but both of those are equal to 1, so why write it? Exactly. Plus f prime, the third derivative, that's what I'm trying to say, over 3 factorial. I forgot the x squared on this one, x cubed, and then we need one more. Man, I didn't leave myself a lot of room. Fourth derivative evaluated at, why did I say 3? My God, what's going on here? Over 4 factorial times x to the fourth. Okay, so now all we got to do is just fill in all of our numbers here, which is going to be a piece of cake because they're all just 1s. Yeah. All right, so that means that our fourth degree Maclaurin polynomial is equal to 1 plus that f prime of 0 is just 1x plus a 1 over 2 factorial times x squared, but we usually just write that as x squared over 2 factorial, plus, and then we've got a 1 over 3 factorial times x cubed, which again, we usually just write that like so, and then finally the last one's going to be x to the fourth factorial, no, x to the fourth over 4 factorial. So there you have it. There is the fourth degree Maclaurin polynomial. What we're going to do in this lesson is that we're just going to keep going with this. What if, for example, we just went dot, 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 dot forever? So then we would have an nth term, right? So what is the nth term here? So notice that like this is plugging in 0, this is plugging in 1, this is plugging in 2 and 3 and so on. And you can see that the n value determins not only the factorial, but the power there. So that would be something like the summation from n, well, no, the nth term. the nth term would be x to the nth power over n factorial. And then if you wanted to, say, sum all of them together, which is what that's doing, and you do that with the summation notation. And if you look at this, this is essentially a power series, right? It is a power series, but it's a very specific power series called the Maclaurin series. Okay, so let's take a look at the next warm-up exercise because we got time for another one. It says, oh, this is weird. Evaluate a definite integral from 0 to 1 of e to the negative x squared dx. All right, I'm not real sure what this has to do with the Maclaurin polynomial thing, but we'll go with it. Okay, so what we need to do here, I think, here, let's try some u substitution, because it is a composite function, right? So maybe the u should be a negative x squared, and then your du would be a negative 2x dx. And while you can fix the negative 2 here, you could never fix the x. All right, so then you go, well, maybe I can do integration by parts, limit, right? And we're at the e, the exponential that's right there, and for one part of it, but what do you use for the other part? There's nothing left over. And you're actually stuck because this thing has what we say is no closed form antiderivative. There's no elementary antiderivative, elementary function, like it's another e to the x, or it's a sine or cosine or tangent. There is no easy way to find its antiderivative. So what we do is that we approximate it with a series. So let me give you a preview of basically what the whole entire unit is about. It's what the goal of the whole entire unit was aiming towards. So if I go back over here, remember that we had ourselves a Maclaurin polynomial, fourth degree, for e to the x. I should be able to do some sort of composition on this thing to get e to the negative x squared. Whoops, no, that should be a negative x. There we go. Right, I do a composition, and we saw from the previous lesson that we can form ourselves another power series by just doing this composition here. So we would just plug in a negative x squared for each one of these. And then we would take the definite integral of that, this whole entire thing here from 0 to 1, and really it's just a whole big polynomial with respect to x, which is easy enough to do because you're just using the power rule, and you don't have to do it forever because that would take a while. Instead, you just want a certain degree of accuracy, so maybe you just do the first 4 non-zero terms, something like that. And as a matter of fact, when we plug in the negative x squared, it turns this thing into an alternating series, which we know, alternating series, we know a way to come up with the error bound very, very easily. It's just the next neglected term or the first neglected term. So it would give us a way to bound the error pretty easily, which brings us then to the point of the lesson here, being able to represent a function with a power, a Taylor, or Maclaurin series, because sometimes these functions are very hard to work with, but polynomials, those things are very easy to work with, so I'm just going to kind of trade one for the other one, and then I could do things like take the antiderivative, or maybe even evaluate a limit, evaluate a definite integral, things of that nature.